Okay, so I wanted to start with this application that we were doing when we ran out of time, just to make sure everybody understands that. So the position of an object moving upward or downward under the influence of gravity is expressed this way. S of t is equal to negative 1/2 gt squared plus v sub 0 t plus s sub 0, where t is the time of travel of the object, g is the acceleration due to gravity, and v sub 0 is the initial speed of the object, and s sub 0 is the position when you start. How many feet above the ground is the object? So this problem gives us all that information. Toy rocket shot straight up from the launch pad 1 foot above the ground, so that's S sub 0. And then initial speed is 64 feet per second, so that's V sub 0. And we want to write the model to express the vertical position of the object S of t. So S of t, we're just plugging in what they gave us into that function we started with. So negative 1/2, 32 is feet per second squared for the acceleration due to gravity, t squared plus 64t plus 1. All right, so we want to know, in part B, determine the time at which the rocket is above a height of 50 feet. So we want to know when the position of the rocket, S of t, is greater than 50. So we're going to write it that way. So negative 1/2 times 32 times t squared plus 64t plus 1 is greater than 50. All right, so we can't really work with it looking like this. We need to get everything on one side and get 0 on the other side so that we can talk about when that value of that function is positive. So subtract 50 on both sides, and you end up with this. Negative 16t squared plus 64t minus 49 is greater than 0. So to figure out where, on what intervals for t, that function is greater than 0, we're going to have to figure out when it equals 0. So we have to use the quadratic formula for that because this is not factorable. So we're going to punch that into the quadratic formula right there. And when we do that, we're going to have negative 64 plus or minus square root of 960 over negative 32. And we are going to punch that into our calculator because this is a real life problem and we want to know basically around how many seconds. So we know then when we punch this in, we get two values, 1.03 seconds and 2.97 seconds. So at those two values of t, negative 16t squared plus 64t minus 49 is equal to 0. So those are the zeros of that function. So we are going to look on the intervals between the zeros to see when this function is greater than 0. We're going to set up our intervals for these values. So we're going to go from negative infinity up to 1.03. We're going to go from 1.03 up to 2.797, and we're going to go up from 2.97 to infinity. All right, so for that first interval, we're just going to check a t value and put it into the function we have right there, negative 16t squared plus 64t minus 49. So we'll pick 0 because it's in the interval and it's easy. So negative 16 times 0 plus 64 times 0 minus 49 is negative 49, and that is not greater than 0. So this interval is not a place where this function is greater than 0. All right. And then the next interval is 1.03 to 2.97. And we're going to pick 2 because that's in that interval. And we're going to put it into this function, negative 16t squared, etc., that we're trying to make greater than 0. And when we multiply that out, we get 15, which is greater than 0. So this interval has that function being greater than 0. The last interval, 2.97 to infinity, we can choose 3 because it's in that interval, and we're going to plug it into this function. And when we do that, we get that it is negative 1, which is not greater than 0. So the interval that's going to work is between 1.03 and 2.97. And so we can see that if you drew the parabola that we started with, you would see that at 1.03 seconds, the rocket is at 50 feet. And at 2.97 seconds, it's at 50 feet. And between those two values, it is above 50 feet. So The rocket is above 50 feet when the time is between 1.03 seconds and 2.97 seconds. Okay, variation. Let k be a non-zero constant real number, the statements on the left are equivalent to the equation on the right. Y varies directly as x, means the same thing as y is directly proportional to x. And if we know that y varies with x in that way, we can write the equation y equals kx, where k is some constant. Y varies inversely as x, or y is inversely proportional to x. Those mean the same things. If y is k over x, for k being some constant, and the value of k for each situation is called the constant of variation. Another name for k is the constant of proportionality. All right, so example 1 says write a variation model using k as the constant of variation. For the amount of medicine A prescribed by a physician varies directly as the weight of the patient. So we would say that A is equal to K times W because this is a direct variation. All right, the frequency F in a vibrating string is inversely proportional to the length of the string. So that means that the frequency is equal to K over L because we're talking about inverse proportion. And then the variable y varies directly as the square of x and inversely as the square root of z. So in this kind of situation, you have some things varying directly and some things varying indirectly. So y is equal to k times x squared because y varies directly as x squared, and then over the square root of z because y varies inversely as the square root of z. Another kind of variation is joint variation. Let k be a non-zero constant real number. The statements on the left are equivalent to the equation on the right. So y varies jointly as w and x, or y is jointly proportional to w and x if y equals k times w times x. And so that's how we would set up a joint variation. Write a variation model using k as the constant of variation. Y varies jointly as t and the cube root of u. So we would set that up. Y equals k times t times the cube root of u. The gravitational force of attraction between two planets varies jointly as the product of their masses, so m sub 1 and m sub 2 we could call them, and inversely as the square of the distance between them. So this is how you would set that up. Okay, so we're going to do an example. The amount of an allergy medicine that a physician prescribes for a child varies directly as the weight of the child. M is equal to KW. And they also tell us that if the amount of medicine that goes with a 30-pound child is 13.5 milligrams. This lets us find K. We just divide both sides by 30, and we find out that K is 0.45. And so now we're going to use that information to figure out how much we would give to a 50-pound child. So we just say the amount is equal to 50K this time. So K is 0.45, so the amount is 22.5 milligrams. And then for part B, we want to know how much you would give a 60-pound child. So we're going to punch that into the calculator, 60 times 0.45, and that's going to be 27 milligrams. And on this last part, they are telling us the prescription and asking if that is what weight child would get that prescription. So 18 milligrams is our amount, and we're looking for the weight of the child. So 18 is equal to 0.45, which is K times W. And so the weight is 18 over 0.45, which is 40 pounds. Okay, example 4, the loudness of a sound measured in decibels varies inversely as the square of the distance between the listener and the source of the sound. If the loudness of a sound is 70.92 decibels at a distance of 10 feet from the speaker, what is the level 20 feet from the speaker? So we have this variation. Loudness is inversely proportional to the square of the distance from the speaker. And so they tell us that it's going to be 70.92 decibels when you are 10 feet away from the speaker, which gives us a K value of 17.92 times 100, which is 1,792. And so now they want to know what's the loudness going to be if you move to 20 feet away from the speaker. So we're just going to plug that in. The loudness is equal to K, which is 1,792 over 20 squared. and that brings the decimal count down to 4.48. So just moving 10 feet further away from the speaker is knocking down those decibels a lot, like almost one fourth of what it used to be. So good thing not to sit too close to the speaker. Really protect your hearing, especially if you are interested in continuing to play or sing for the rest of your life, because you do not want to mess up your hearing. And even if you don't know it, sitting too close to a speaker or putting your earbuds up really loud will damage your hearing. That's my public service announcement for now. All right. Solving an application involving joint variation. So meteorologists define hurricane season for the northern Atlantic Ocean to be from June 1st to November 30th. During this time, residents in the Caribbean islands, Central America, and the eastern seaboard and Gulf Coast of the United States watch tropical weather forecasts with intense interest. These first storms bring deadly storm surge, damaging winds, and physical economic destruction to the areas they hit. The winds of a hurricane are strong enough to send a piece of plywood through a tree, and you can see that right there in that picture. It's kind of amazing, but that is done by the force of the wind. So the kinetic energy of an object, that is the energy that a body possesses as it's flying through the air. That board had a certain amount of energy stored up in it that the tree, that energy was spent on that tree, you can see. So the kinetic energy in an object varies jointly as the weight of the object at sea level and as the square of the thing's velocity. So during a hurricane, a zero point 0.5 or half-pound stone traveling 60 miles per hour has 81 joules of kinetic energy. Suppose the wind speed doubles to 120 miles per hour, find the kinetic energy of that same stone. So we're going to set this up according to what they tell us. The kinetic energy in that stone is equal to K, some constant, times the weight of the stone times the velocity squared. And so they tell us that we have 81 joules of energy when the stone is half a pound and traveling at 60 miles per hour. So that's going to give us a K value of 0.045. And so we can plug that in now that we're saying the wind speed has doubled to 120. So we're just putting it all in there with a new wind speed of 120 and the K value of 0.045. And when we do that, we are going to get that the energy in whatever that rock is 324 joules.